In this video, we're going to run through a couple problems that relate to 3D static equilibrium of rigid bodies. So our first problem here is asking us to find the x, y, and z components of the reactions at hinge A and the tension in cable BC. Okay, so let's draw a couple things out. So tension cable in our BC is going to be pointing in this direction. We are shown that there is an angle. So we can use some of our knowledge from our, I believe, week 2 or 3 knowledge. So this is BC. Okay, and A, we cannot translate this in our X, Y, or our Z directions. So we have AZ, AX, and AY. And we have some moments to consider. So we can rotate this body about our x-axis, so that means we are going to develop our z-axis and in our y-axis. Let's assume clockwise directions for either of them. So if you look down the positive barrel of each axis, it would look like it was rotating clockwise. Okay, for sake of the answer key, I'm going to change this BC into T for tension. And we have a certain angle. So this isn't just in line with our y-axis, our tension. So I'm going to actually start with that. Let's start with our tension. So we don't know the value for our tension, but we could start by getting into a Cartesian form. Okay, so we are going from point B to C. So B is 0 in our Z. In our X, it is 1.2 in our negative X direction. And in our Y, our distance is positive, and that's 1.8. And for point C, we are at a height of 0.6. We haven't translated anywhere in our Y. And we are negative 0.3 from our x-axis, from our origin, sorry. So we want to find our position vector for BC. So this is equal to, so that's C minus B, so that's negative 0.3 minus negative 1.2, and that is 0.19. In our I direction, this is minus 1.8 J, and this is plus 0.6 K. Okay, and now we're going to find our unit vector, which is 0.9 I minus 1.8 J plus 0.6 K. That's over the square root of 0.9 squared plus 1.8 squared plus 0.6 squared. So that's 0.9 squared plus 1.8 squared plus 0.6 squared. And this is 2.1, so 0.9 divided by 2.1 is 3 over 7. This is minus 1.8 divided by 1.2. This is 3 over 2. j, and 0.6 divided by 0.2, this is 0.5. So this is 1 over 2. Sorry, this is 2.1 at the bottom. Let me just change that. 1.8 divided by 2.1 is 6 over 7. Okay, and our last one is 0.6 divided by 2.1. This is 2 over 7. Okay, so that means our Cartesian form of our tension is equal to the magnitude of our tension force, and that's 3 over 7I minus 6 over 7j plus 2 over 7k. Right, so that makes up our x, y, and z components. If we want to just draw the directions really quick, in our x direction we are positive, in our y direction we are negative, and our z direction we are positive. Okay, so that is tension sorted out using our knowledge from week 3 of our equilibrium equations and using unit vectors and position vectors to find Cartesian forms. Okay, so let's start with our equations. So x, we have, also need to add this weight here. And our weight is 1500 newtons. It's given to us. Okay, here we go. So this is AX, and this is plus our T 3 over 7. We've got two unknowns. It's equal to 0. Fy is equal to 0. So this is equal to AY and minus our 6 over 7t. Okay, and in our z directions, we've got positive A, so AZ, positive. We've got positive tension, so this is T times 2 over 7. And we have in our negative direction, we have our weight. Okay, so those are all of our force equations. Scrolling down, I'll zoom out a little bit so I can still see. So for about our x-axis, all of the A reactions intersect it. So we can use our 1500 newtons. Let's just start with that. It's equal to, and this is acting in the z direction. We want to go to our x direction, so that leaves y distance. So that is 1.8 meters. Right, and using our right-hand rule, we see that it points in the negative x direction. We can't use this one because it's parallel to our x-axis, but we can use our other two components and their respective directions. So this is our y component. This is t 6 over 7. And this is our distance is going to be our z distance. Sorry, this is our x distance we need for that. Right? Hold on. Sorry, I lied to you. We can't use our y component because it's going to be going through our x in the line of action, so that leaves us just with our z components. That's t 2 over 7, and we want our y distance, and this is in our positive x direction. Okay, now I'm going to do our y. Let's eliminate what we can. So I'm going to write this moment because I will forget. Okay, so we can't use any of our A reactions. We cannot use our tension y because it's parallel, and we can't use our tension x because it would be going through the y-axis. So we can use our weight, and we can use its distance from the y-axis, which is 0.6 in our x direction. So this is 0.6. And if we used right-hand rule, this would be pointing in the negative y direction. And we can also use our tz. So this is t2 over 7. And this is at a distance of 1.2. And this is in our positive y direction. All right, so for about our z, just going to leave some room here. We have, so we can't use any of our A reactions. We can use this moment about our z, so I'm going to write that in or else I will forget. All right, and we have our, so we can't use our weight, we can't use our z component, and we can't use our z component for A either, because they are all parallel to our z axis. So we can use both of our components for t, for our x and our y directions. So that leaves us with, so it's t 3 over 7. This is our x component. So x and z, that means we need our y distance, which is this is 1.8. And this is in our, so we point along, that gives us negative direction. And we have our y component for t, so this is t 6 over 7. And this is times, so this is our y component. We want z, so that leaves our x distance. So our x distance is 1.2 meters. And this is in our positive y direction. Sorry, positive z direction. Okay, so now we can start solving. So I'm going to start solving for moment at x because we have one unknown, so we can solve t first. And that means we can solve for our moments. So this is, when we move that to the other side, this is so it's 1500 times 1.8. This is 100. Okay, and we can divide by our 1.8 from our other side. And we can multiply our 7, divide our 2, and this should be 5,250 is equal to our t. So let's check our answer. Yep, and that is correct. So now we can start solving for our other values from our moment equations because we just have our moments. So this means our moment at A, our y-axis, is equal to So this is positive 1500 times 0.06. So this is 900 plus T 2 over 7 times 1.2. Okay, and we know our value for T. So this is 900 plus our value for T is 5,250, and that's times 2 over 7, and that is also times 1.2. This is equal to 2,700 Newton meters for our moment. Moment AY. Let's check our answer. Okay, wonder what went wrong. I know what went wrong. To minus. Okay. So this equals, so it's 900 minus our T. So this is 5,250 times 2 over 7 times 1.2. And this is negative 900. There we go. It's negative 900. So this means this is going to be clockwise. So I'm just going to leave it like that. All right, and our MAZ is equal to, so let's be careful with the signs this time. Let's change the sign for this one. Change the sign for that one. And when we plug in our value, this gives, so 5,250 times 3 over 7 times 1.8. And this is minus 5,250 times 6 over 7 times 1.2. And this is negative 1,350 Newton meters. Let's check our answer for this one as well. Awesome. In our negative Z direction. So both of these negative values mean that we just didn't assume the correct direction to start with. Okay, and that makes solving for our AX simple. So then AX is equal to, so then that's 5,250 times 3 over 7, and this is negative 2,250 newtons. AY is, so we move that to the other side, and this is times 6 over 7. This is positive 4,500 newtons, and AZ is equal to 0. Okay, so let's check our answers. AX, yes. AY, yep. And AZ. All right, so that is this question done. Okay, so we're going to work on this last one here. So a vertical force of 350 newtons acts on the crankshaft below. Determine the horizontal equilibrium force of P that must be applied to the handle, and determine the X, Y, and Z components of the force at the smooth journal bearing A and thrust B. And the bearings are properly aligned to only exert force reaction, so there's going to be no moment reaction. So it's kind of like the last example that we did from our notes video. Okay, so let's just check our notes just to be sure. So we have a smooth journal bearing. So smooth journal bearing, this was like our pencil sharpener. So this means we can move it along the y-axis, so we're going to have a z and an x reaction. And for B, a thrust I believe we can't move through, so let's just check. Oh, single thrust bearing, let's see. So yeah, so this is as if it were fixed at the end, so we can't move through. So this means we develop 3 reactions. Oh, where are we? There we go. So this means we have BZ, BX, and let's say this is BY. All right, so we have 1, 2, 3, 4, 5 unknowns, and 6 makes our P. So we're good. We don't have too many unknowns. We can solve this. Okay, so let's start with our X reactions. So this is our, so let's say this is positive. So this is AX plus BY, sorry, plus BX, and then minus our force P. Let's do that in blue. Okay, and Fy, we have AY, actually no AY, just BY. So right off the bat, we can say By is equal to 0 newtons, because that's the only value we have. Okay, and our sum of Z is equal to 0. So then that is our negative 350, which is given to us, d newtons. Let's not put that in there. And then we have positive AZ and positive BZ. And yeah, that's pretty much it. So that's it for our force reactions. And now let's do our moments. So we have, okay, so we can't use P because that is parallel. We can't use AX, it's parallel, BX is parallel, and BY goes through, and so does AZ. So we can only use our BZ and 350 over here, right? Because the rest, okay, so again, BX, AX are parallel, BY will end up going through it, and AZ also goes through it. So then we can only use these two, and P is also parallel. So this leaves us 350 is acting in our Z direction. We want to find it to our X. This is our Y distance from it. So Y distance is 300 millimeters. So this is 0.3 meters, if I'm not mistaken. Okay, that's right. And this is in our negative X direction. Okay, and if BZ is positive, this is BZ. And we want our Y distance, so this is 0.6. And this is in our positive X direction. Okay, so let's solve for BZ while we're here. BZ equals, so that's 350 times 0.3 divided by 0.6, and this is positive 175 newtons. So that is 2 of our answers down now. Okay, still a few more to go. Let's check our answer. BZ 175, awesome. Okay, and about our z-axis, this is equal to, sorry, y-axis. Did I say y or z? I'm not sure. Okay, so this means we can use our So we can't use by, and we can't use our anything here, so we can't use this, can't use this. So that leaves us with, okay, BZ also goes through, so we can't use that. That goes through our y-axis. So that leaves, this goes through, that leaves our external force and our P. So we can solve for P right here. So this means 350 newtons is in the z direction. We're measuring at our y-axis, so we want our x distance, which is 0.25. Okay, and this is in our negative y direction. And we have our force P. This is P in our x direction. So we want our z distance, so this is 0.175. And this is in our negative y direction as well. Okay, so now P is our only unknown in this example. So this is P is equal to negative 350. So it's 350 times 0.25 divided by 0.175. And this is equal to negative 500 newtons. And we can check that. And that is correct. Okay. And our final one is in our, about our z-axis. So do this in a different color so it will be a little better. Okay, so what can't we use? We can't use that because it is parallel. That's parallel, that's parallel. This is through. This is going to be through. This is not going to be through, so we can use that. And this is not through. So we're going to be solving for bx in this equation. So this is, so bx is in our x direction, and we're measuring both z, so we want our y distance, which is 0.6 meters, and this is in our negative z direction. Okay, we have our force of P, which we already have, so this is P. We are in our x direction, we're measuring about our z-axis, so we want our x distance. Sorry, our y distance, which is times 125 plus 100. This is 225. And this is in our negative z direction as well. And if we solve for bx right here, bx is equal to, so our p is 500 times 0.225 divided by 0.6. This is negative 187.5 newtons. Let's check. Awesome. This is also correct. Okay, and now let's just go back to find our forces. So let's find AX here. So AX is equal to, so that's P minus BX. And we found BX over here, so that's going to be positive 187.5, and that's minus, hold on, let's write this out. So this is minus negative 187.5, and this is plus our P, which is 500. So this is plus 500, 687.5. which is consistent with our answer key. So that is good. And then we found by, so let's just find az is equal to negative bz plus 350. Az is equal to, bz was 175. So that's negative 175 plus 350, and that is 175 newtons. Okay, so some of these problems are quite long. They do take a bit of time to get through, but it's important to take your time for these questions in particular. You want to be very careful and make sure you don't miss any moments that are being developed, and you input your equations correctly. And we also did an example that kind of mixed some knowledge from previous units. So also be sure to remember how to use these skills to find different forces and different components of forces to break it down even further to make it fit your equations and make it a little simpler to understand. Okay, that is the end of this video. Thank you for watching, and I will see you in the next one.